Welcome back. Let's continue on the curve sketching. This is the part 2. So last time we've discussed mostly how to graph functions. This section I'm gonna introduce something called slant asymptote. But first, let's see what is the slant asymptote through a graph. Let's assume you have a graph of f of x. If I ask you what is a horizontal asymptote, you'll notice that this dashed line where the graph approaches to the infinity, that would consider as a horizontal asymptote. Slant asymptote, instead of having a horizontal line, what you have is a straight line, and the graph of the function f somehow approaches to that line. So this is the function f, and this is a line y equals mx plus b. The line y equals mx plus b is called the slant asymptote for the function f, because f, as x value grows toward infinity, the y value is approaching to this straight line. So you expect the behavior as you go further to be very close to this straight line. So what we can say is, in the infinity, as x is getting larger, the difference between the function f and the y value in the line are going towards 0. So that's what we're expecting of the definition. The slant asymptote by definition is the difference between the function and the straight line y equal mx plus b as x approaches to infinity or negative infinity. If it approaches the other way, toward negative infinity, then the difference between these two is approaching 0. So you expect the limit to be 0. Okay, there are multiple ways to calculate slant asymptote. Best way is to try to subtract from a straight line and figure out what is the coefficient m and the constant, so the slope and the y-intercept. Not every function has slant asymptote. Normally it happens to be for polynomials if the degree is 1 higher. Here's an example of it. I'll show you 2 ways to figure out the slant asymptote. One way is through the long division. So first let's go through the process of graphing, because we're going to do the graphing and we will calculate the slant asymptote instead of horizontal asymptote. So here, graph f of x equals 2x cubed divided by x squared minus 1. Again, f prime and f double prime, you can calculate those through quotient rule. The first thing you should notice, always find the domain. The domain of f, all real numbers except the points that makes the denominator 0, which is in this case plus or minus 1. X squared minus 1 equal to 0 gives us x equal to 1 and negative 1. We exclude these 2 points. Okay, after finding the domain, we look at the intercepts. What is the x-intercept? What is the y-intercept? Which means, where do you get 0 for x, 0 for y? You replace 0 for x to find out the corresponding y value for the y-intercept. By doing that, y will become 0. You replace 0 for y, that means let the function equal to 0. So you have 0 equals 2x cubed divided by x squared minus 1. And what you get is the numerator must be 0, therefore x is 0. So you can find out the x-intercept and y-intercepts are the origin. Okay, after finding the intercepts, we look at the vertical and horizontal asymptotes or symmetry. Which order do you want to do it? So let's try symmetry first. Find out f of negative x. What do we get is replace negative x into the function. 2 negative x cubed divided by negative x squared minus 1, which is simply negative 2 x cubed divided by x squared minus 1. What is the relation between f of negative x, which is this term, with f of x, which is that? See that it's exactly the same function multiplied by a negative. So I can say it is the same as minus f of x. So f of negative x is the same as negative f of x. This means f is an odd function. F is odd, which in our symmetry property is, that means f is symmetric about the origin. It means whatever you graph on the right side, the origin, you would have exactly the same thing symmetric about the origin on the other side. Okay, on the symmetry, now let's focus on the horizontal and vertical asymptote. Vertical asymptote, we'll look at those two excluded points. X equal to 1 is one option, the other one is x equal to negative 1. You figure out the value of the limit f of x as x approaches to 1. Replace 1 into the function, what you get is 2 divided by 0. Again, this is, in limit sense, this approaches to infinity, either positive or negative infinity, one of those two. That means x equal to 1 is a vertical asymptote. If you try negative 1, you'll get negative 2 divided by 0. Again, that would be positive or negative infinity. So this is a vertical asymptote, both 1 and negative 1. And then what we can do next step is find the horizontal asymptote. Calculate the limit. You write it on the side. Limit f of x as x approaches to infinity, either positive or negative infinity, which means limit 2x cubed divided by x squared minus 1 as x approaches to infinity. Let's try positive infinity, negative infinity is the same. X approaches to positive. And the technique was to divide by the largest term in the denominator. 2x cubed divided by x squared divided by x squared, negative 1 divided by x squared as x approaches to infinity. Numerator simplifies to 2x, denominator simplifies to 1 minus 1 over x squared. As x approaches to infinity, this term approaches to 0. Then what you have is simply limit 2x divided by 1, which is 2x, as x approaches to infinity, which is infinity. Which is infinity. So that means the horizontal asymptote, there is none. Or maybe instead of does not exist, I should say no horizontal asymptote. Because the limit is not going to approach to a constant value. It approaches the infinity. That means if you increase the x value, the y value is going toward infinity. But now if I ask you, do we have any slant asymptote? Since vertical asymptote, horizontal asymptote, the question becomes, do we have any slant asymptote? Best way to deal with slant asymptote is, since you expect the slant asymptote to be a straight line, mx plus p, that means if you find the difference between the function minus that line, in limit sense, you expect to get 0. Means let's ignore that constant b. If you figure out what is m, then by replacing into the function and subtracting it from it, then you can figure out what the value of b is. So our problem first is to find out what is m. How do we do that? Is calculate the limit of the function, divide by an x as x approaches to infinity. This tells you the slope. If there is a slant asymptote, this is how you find the slope. So it means I will calculate limit function, which is 2x cubed divided by x squared minus 1, all divided by x and extra x as x approaches to infinity. You can simplify limit. I can combine all these. The x cancel out with the numerator, so you get 2x squared divided by x squared minus 1. The x approaches to infinity. And if you follow the same procedure as we did above, if you follow this, what you get at the end is 2. Skip over those steps. What you get is 2. So what does it tell us? It says for the slant asymptote, we have a slant asymptote, mx plus b, and I just figured out that the m is 2. So I have 2x plus what is b. Now to figure out what is b, I'm going to calculate the limit f of x minus 2x, and as x approaches to infinity. If I do this, I'll figure out what is that constant b. Change this to a different b. So now let's calculate that. Limit x approaches to infinity. We had 2x cubed divided by x squared minus 1, and I'm going to subtract 2x from it. You need to do common denominator. Give the denominator 1 here. What do we get is limit x approaches to infinity. Multiply same denominator here, which is x squared minus 1, both in the numerator and denominator. What do we get is x squared minus 1, 2x cubed minus 2x times x squared is 2x cubed. Negative 2x times negative 1 is plus 2x. By doing this, you can simplify now. These two will cancel out. You'll get limit 2x divided by x squared minus 1. X approaches to infinity. If you calculate this limit, again, use the same technique that we did above. With the same, this one. Divide by the largest term in the denominator, which is x squared. And what do you get is 0 in this case. So what do I find? I found out that the b is 0. So I found the slant asymptote. What is the slant asymptote? Is y equals 2x plus 0, which is simply just 2x. That means at the end, function is going to approach to this line. At infinity, if you calculate negative infinity, you still get the same result. So on both sides, you will approach to the line y equal to x. And the symmetry will kind of tell you that this happens. This is one way to find the slant asymptote. The other way is do long division. There's one technique. The other technique would be to find the slant asymptote. We can double check by doing the long division. So the function f is given x cubed divided by x squared minus 1. Okay, so let's try to do the long division. You would have x cubed here, x squared minus 1. Whatever you find in this box is going to be the slant asymptote. This is what we're going to figure out. So through the long division, sorry, this was 2x cubed. 2x cubed. Through the long division, I need to multiply 2x squared to get 2x cubed. And 2x times negative 1, I'll get minus 2x. Subtract the top from the bottom. What you get is 2x cubed minus 2x cubed will cancel out. You'll have nothing here, so there is 0 minus negative 2x becomes positive 2x. Can I divide 2x into x squared minus 1? Not really, so there is nothing here but plus 0. So I found out the slant asymptote y equals 2x 0. Long division is a faster way to find the slant asymptote. You don't need to go through these steps over and over. But this is another technique that you could do. Okay, either way is fine by me. You can pick either method. So in this case, slant asymptote, again, you will get 2x. Okay, we found the slant asymptote as well. Now we have the x-intercept, the y-intercept, asymmetry, horizontal and vertical asymptote, slant asymptote. Now we can find the increasing, decreasing interval and local max and mean. The first derivative is given x squared. So actually, you should calculate that x squared times x squared minus 3 divided by x squared minus 1 squared. here, first derivative f prime x was x squared times x squared minus 3 divided by x squared minus 1 squared. Okay, so if this is the first derivative, where is it? So I don't make a mistake. Yes, if this is the first derivative, we need to figure out the critical numbers. Continue blue, the critical number. What are the critical numbers? Zeros of the numerator as well as zeros of the denominator. So x would be 0, x would be plus or minus square root of 3. These are the critical numbers that makes the numerator 0. Means this is when the derivative is 0. And when the derivative does not exist is at plus 1 and negative 1. These two, plus 1 and negative 1, are plus 1 and negative 1 are not in the domain. Again, be careful with these. When I use them on the number line, but the derivative did not exist at those points. I have first derivative, these points in order would be negative root 3, negative 1, 0, 1, and root 3. Big test point in each interval. Try something like negative 2, negative 3 half, negative 1 half, 1 half, 3 half, and maybe here I'll pick 2. Replace these numbers into the first derivative. Figure out what is the sign for it. If you replace negative 2, by the way, denominator is always squared, so it is positive. This term is always squared, so it is positive. You just need to figure out the sign for this x squared minus 3 term. If you replace negative 2 there, you'll get 4 minus 3, which is 1. So this would be positive. If you replace negative 3 half, you'll get a negative number. If you replace negative 1 half, you will still get negative. If you replace positive 1 half, you will still get negative. If you replace 3 half, still negative, and here you'll get a positive. Means function is increasing and decreasing, continue to decrease, continue to decrease, decrease. This is how the function looks like. Okay, and expecting some of these results because they have vertical and horizontal asymptotes. So around these asymptotes, you expect these behavior. This is the asymptote. Okay, so where is the local max and local mean? Maximum is a local minimum. I can say local max because there's a change in the sign, local mean. And it happens to be at the points where the derivative is 0. 0, which was the derivative equal to 0, still have decreasing, so there is no local maximum or minimum at that point. This is the first derivative. If you focus on the second derivative, well, the second derivative is 2x times x squared plus 3 divided by x squared minus 1 cubed. Okay, so 2x times x squared plus 3 divided by x squared minus 1 cubed. So where is this second derivative equal to 0? Critical number for the second derivative is at x equal to 0, and then x squared plus 3 equal to 0 is going to give you x equal to plus or minus square root of negative 3. This is not acceptable, so there is no solution to this. So there is only one critical number, and the other 2 points that makes the denominator 0 are plus or minus 1. Again, not acceptable, but we write them. Draw the number line. Here's the number line for the second derivative. Let me draw this line a bit lower. For the second derivative, and the points are 1, 0, negative 1. test points, I'll pick -2, -1/2, 1/2, and 2. Okay, replace -2 into the function, into the second derivative. What you get is negative here, multiply by a positive number, divide by a positive number. So you get negative times positive, divide by positive, you'll get negative number. Again, you don't need to calculate the number. It's just the fact that figuring out what is the sign is good enough. -1/2, if you replace -1/2, this would be negative, the other term would be positive, divide by a negative number. So what you get is negative divided by negative positive. If you replace 1/2, this is still negative, this becomes positive, so you'll get a negative number. And if you replace 2, you'll get positive times positive divided by positive, everything is positive, so you'll get positive. So what we have is now concave down, concave up, concave down, and concave up. And is there an inflection point? Yes, there is. This is an inflection. The other two are not acceptable because these are vertical asymptotes. They do not belong to the domain, so they cannot be inflection point. Okay, let's put all these information in one table. Okay, go. F prime, and F double prime. The important points to be found was -√3, -1, 1, 0, 1, and √3. It's necessary to find the corresponding y value as well. If you replace -1 and 1, these were vertical asymptotes, so there is no y value. For √3 and -√3, they were local max and mean. So how do I find the y value? You go back to the original function, replace √3 into that, and replace -√3. If you replace √3, what you get is 2 times 3√3 divided by 3 minus 1. You get 3√3. You get 3√3, and the denominator is again 3√3, but negative. Okay, so this is just simplified y value. I replaced it in the original function. Vertical asymptotes, these are local maximum or local minimum, and 0. We found out 0 was an inflection point. So here, inflection point. I'm going to write local max or mean. We look at the graph. Let's figure out. -√3 was local max. This is a local max point, and here you should have a local minimum. Okay, now put the increasing and decreasing interval. So you have increasing, decreasing, decreasing. You have increasing, decreasing, 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 and increase. This is exactly this number line for the first derivative. The second derivative, you have concave down to -1. Again, concave down to -1. So I'm going to stop at -1. Here's -1. Everything on the left side of -1 is concave down. Even though it's two section, √3 would be somewhere here. Doesn't affect the fact that it's concave down. After that, concave up to 0. 0 to 1 is concave down. And after that, concave up in both sections. So now, graph. Combining these two information, increasing plus concave down. What does that graph look like? That graph would be something like that. And decreasing concave down, be like that. Decreasing concave up, here's the shape. And again, concave down, decreasing concave up, and increasing concave up. So now we just need to attach these curves together again. Let me graph this nicely. Here's the graph of vertical and horizontal asymptotes first. 1, -1. We have vertical asymptote. At these 2 points, you have vertical asymptote at the 1 and -1. Okay. Local max and mean, -√3. That happens at -√3 and √3. So here's -√3, and their y value is -3√3 and +3√3. We have this point, which is going to be a local maximum, as well as at √3, we have this point, which is a local minimum. It's important to figure out the local max and local mean as well. Okay, what is the slant asymptote? Since you don't have a vertical asymptote. Slant asymptote was y equal to 2x. So it's a straight line. Try to graph it with yellow maybe. The straight line y equal to 2. Something like let me come back to the slant asymptote because I want to make sure that we will see how it approaches to the curve. Maybe it's like this. This is y equal to 2x. Okay, that was our slant asymptote. It's good to pick a couple of points on the slant asymptote. Show it. Okay. Okay, we had 1 point as a part of the curve, 0, 0, and we do not cross the x-axis or y-axis anymore. That's the only time that we cross the x. So now let's continue graph this. You should draw these curves from curve 1, 2, 3, 4, 5, and 6 in order. Start from 1. You have an increasing function. You should approach this point, and you should be close to the slant asymptote, something like increasing concave down, like this. It's better than what I drew. It's a concave downward. It's not a straight line, so it's kind of curved downward. And then this is section 1. Section 2 from √3, from -√3 to -1, we have a concave down and decreasing, approaching to the vertical asymptote. And graph 3 would be from the vertical asymptote to 0, from the vertical asymptote to 0, concave down, concave up but decreasing. If you graph this side by the symmetry, you should be able to graph the rest. But if you don't have the symmetry, you should still follow those sections. Symmetry will help you through the origin. Symmetric. So what do you expect on the other side is and you notice that we have a local minimum here and a local maximum at that point. And the only time that we cross the x-axis is at the origin. So this is a well-detailed graph for the function f of x. Okay, the problem with doing example for this section is it takes too long to go through all the details precisely. But I've done 3 examples. The slant asymptote is the only thing new compared to what we've done already. And you've seen 2 methods. I've shown you 2 methods to find the slant asymptote. You can pick either way. You can calculate through the limits, or you can do long division, whichever looks simpler. And what you expect is always to have slant asymptote is something linear. If you have 2x squared, for example, that does not consider as a slant asymptote. It's just a function, asymptotic function. It's not going to be a linear function. Okay, so this is good enough for this section. I'm going to stop here and we'll continue on optimization next time.